All right, ladies and gentlemen, class recording for today has begun. So, over the past couple weeks, we have spent a lot of time talking about mechanical waves. What qualifies something as a mechanical wave? Okay, go ahead. Transfer of energy through a medium, right? Mechanical waves need a medium to travel through. And we talked about the different kinds of mechanical waves, transverse, longitudinal. We talked about the wave behavior, reflection, refraction, blah, 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 blah. Some of that stuff applies to electromagnetic waves, some of it doesn't. But, so, the one thing, though, that I want to start us with is, at its nature, or at its core, mechanical waves and electromagnetic waves relate to the types of energy transfer that we talked about back in the heat energy unit. So we talked about 3 ways that energy can be transferred. We were talking about heat energy. Do we remember the 3 ways of energy transfer? Give me one of them. Eris, what's one of them? Conduction, right? So let me go here. So we talked about that there was conduction, right? And Eris, what was the big gist of what's the most important part of conduction? Direct contact, right? All right. Second method of energy transfer. Radiation, right? So we'll throw this down here, right? And then Jotham, radiation. The big gist of radiation is what?
Travels through space.
Travels through space. And these 2 here really are sort of theory behind the different types of waves. Conduction, this is pretty much how mechanical waves work. That there's direct contact, and that one part of the medium touches the next part of the medium and transfers energy there to there. Then that part touches the next part, energy transfer there to there, and on down the line. But radiation, this is where we start getting into electromagnetic waves, or EM for short. So when we talk about the different types of energy transfer, it has some application here. This is how those types of energy transfer occur. So with that being said, let's go over some definitions. Some of these we talked about at the beginning when we first introduced waves. So, electromagnetic waves. Electromagnetic waves are transverse waves consisting of changing electric fields and magnetic fields. We'll get into that in a little bit more detail here in just a second. But changing electric fields and magnetic fields. As far as the comparing and contrasting of mechanical waves and electromagnetic waves, let's go here. Electromagnetic waves transfer energy without transferring matter, meaning that they do not need a medium to travel through. Right? They will travel through empty space. They will travel through a vacuum. That's how we get all of our energy from the sun, right? There's nothing that fills the space between us and the sun, but energy still gets here. All right, in another type of comparing and contrasting thing, we said that what has to happen in order for a mechanical wave to start? What starts a mechanical wave? Or how do we get a mechanical wave? Nick, go ahead. Something has to do work, and especially has to do work on what? On the medium. Right? That's how a mechanical wave starts. Electromagnetic waves are similar to that, except instead of doing work on the medium, we're going to do some work on a charge. A lot of times it's electrons, but it doesn't have to be. There has to be some change in a charged object. And earlier in this class, we talked about that there are 2 types of charged objects, right? You got protons that are positive charged. You got electrons that are negatively charged. As those electrons or other charges, electrons or protons, move around, that creates the wave. Right? If you go back to atomic theory, way back chapter, I think it's the 3rd chapter we did in this class, we talked about a Bohr model for an atom. Anybody remember what a Bohr model looked like? There's
One with all defined shells.
right. So it looks kind of like a mini what?
Planet. Or solar system.
Yeah, it kind of looks like a mini solar system, right? And we said that the gist of the Bohr model was it has the defined shells, so electrons can exist in those defined shells but nowhere else, right? But we also said that those shells relate to what about those electrons? What did those shells tell you about the electrons? How much energy they had, right? So Mark, lower energy electrons were where?
Closer to the center.
And then higher electrons energy farther away, right? We said that electrons could jump levels. You could go from a low level to a high level if you gained energy. And you could go from a high level to a low level if you lost energy. That happens through electromagnetic waves. A lot of times those electrons will gain energy by an electromagnetic wave hitting them, and they will jump up to a higher level. But we talked about that they don't like being in that higher level, so they fall back down. And as a result, they give off energy in the form of electromagnetic waves. That's what's going on with these lights in this room. Those electrons are gaining energy from the electricity that's coming from the outlet or from the power station, wherever it is. So they gain energy and they jump up to a high level. But they don't like being in that high level, so they fall back down. And they give off that energy in the form of electromagnetic radiation, specifically visible light. Okay? Good there. All right. Let's, before we go on to the next part, this first definition, transverse waves consisting of changing electric fields and magnetic fields. This is what an electromagnetic wave would look like if you could kind of see it, but it's hard to see the actual wave itself. We see more the effect of that wave as opposed to the wave itself. So this looks like a big jumble of arrows and dotted lines, and it kind of is. But you have to think of it as a two-dimensional representation of a three-dimensional wave. A transverse wave, we said, vibrates which way in relation to the wave movements? Perpendicular, right? So it can either go up and down, or it can go side to side as the wave is traveling forward. What happens with an electromagnetic wave is that there are actually two waves. One of them is electric, one of them is magnetic. And one of them vibrates up and down as the other one vibrates side to side. So it's kind of hard to see from this picture, and if you're listening to the recording, you can't see it anyway, but if we think about it this way, right? As one goes up, the other one goes to the side, and then they come back together. And then as one goes down, the other one goes to the left, and they come back together. And then up and to the right, back together, down and to the left, back together. It's almost like two snakes that are sort of like weaving in and out of one another. Is that kind of sort of maybe? Do you have some sort of a picture in your head as far as what that looks like? So those two waves make up the electromagnetic wave. Like its name suggests, one of those waves is an electric field, one of those waves is a magnetic field. Now, we have briefly discussed fields previously in this class. We talked about them in terms of electricity and magnetism. Does anybody remember what a field is? That's a tough one. A long time ago. So let's go here. Picture I showed you right there is a picture of what? Take a guess. It's a picture of two objects. The one on the left is a feather. The one on the right is an apple. You guys actually have a copy of that picture on your outline. Okay? What are those two objects doing? It's like a time-lapse photography. This time-lapse picture shows the position of these objects at every 1/10 of a second or something like that. So what are these two objects doing here? They're falling, okay? And hopefully we know that they're falling under the influence of gravity. Yes? And we'll learn all about gravity in a couple of weeks and how it affects things, stuff like that. But the gist being that they go faster and faster and faster under the influence of gravity. But the weird thing about gravity, among other things, is that it can make objects move without actually touching them, right? There's nothing that touches this roll of tape in order to make it do that. It happens without contact. That's a field force, something that can change the motion of another object even though there is no physical contact. Right? Certain forces have the ability to change the motion of other objects even though there is no physical contact. The area around that object where it can affect other objects, we refer to, oh, sorry, this picture here. Some of us may have done this before. Some of us have the ability to do it. Some of us don't. You know. But you take that balloon, you rub it on your existed hair, if you have hair, and you can get that balloon to cause your hair to move, blah blah blah. But then you can also cause that balloon to stick to the ceiling, right? And all fun things like that. Okay? Even though this hair is touching the balloon in this picture, you've probably experienced the fact, like in the winter time, if you take off a sweater or something like that, your hair can move even though maybe your sweater doesn't actually touch that hair, right? That idea that certain forces can change objects even without touching them. Or, most of you have probably played with magnets before, right? One magnet caused the other magnet to move, and we talked about that back in the E&M chapter, right? North Pole, South Pole, all that fun stuff, right? Even though there's no direct contact, we can still get those objects to move. The area around that object where it can cause other things to move is called the field. Right? So the field is an area around an object where it can change other things. All right, how about if I bust one out for you? Are you guys ready for this one? Anybody remember the right hand rule? Man, that was, all right. There's, what? That has to do with your right hand.
If you like wrap your hand around it, where your thumb is pointed,
Okay, so if you wrap your hand around what? Talking about a wire, and that wire is doing what? It's carrying a, what do we call when charges move? We call that a, somebody's trying to whisper it to you. Was that you? It's called a current, right? So if a conductor is carrying a current, right, if a wire is carrying a current, we stick our thumb in the direction that the current is moving, right? And then we wrap our fingers around that wire. And that represents what? Do we remember? That's the important part.
Direction of magnetic field.
The direction of the magnetic field that surrounds that wire. So the electricity has the ability to affect magnets, right? That's an application of a field and a field force. That those fingers represent the way that magnets would behave in that field. So we talked earlier about electric fields and magnetic fields. They are related to one another, right? Electric fields are the areas where forces are exerted on charged particles, positives and negative charges, namely protons and electrons, right? Magnetic field, area where the forces are exerted on magnets. And we said that electric fields affect magnetic fields, and magnetic fields affect electric fields, and all those, they're interrelated to one another. That's why these waves that are carrying energy consist of both an electric field and a magnetic field, because one affects the other. And if you go back to the picture here, as you can see, if the yellows represent an electric field and the blues represent the magnetic field, as the yellow arrows are getting bigger, what do you see is happening to the blue arrows? They're getting bigger too, and as the yellow ones are getting smaller, the blue ones get smaller, because electric fields affect magnetic fields and vice versa. And that's how these waves can travel through nothing. They basically travel through each other. The two waves produce the other one. One produces the other, and the other produces the first. Right? They're intertwined, and that's how they can travel through nothing, because they have each other. Is that a good 10-cent version of what an electromagnetic wave is? Okay with that? All right. So let's get down to business here. Fields. There we go. At the beginning of class, we talked about the idea that electromagnetic waves are basically the mechanism of energy transfer by radiation. So electromagnetic radiation is the transfer of energy by electromagnetic waves traveling through space or matter. So we said that radiation is the transfer of energy without the transfer of matter, which is true. But electromagnetic waves can travel through matter. They don't need to, but they can. For instance, right? If electromagnetic waves couldn't travel through matter, we have a problem in this room, right? This room is full of matter. It's gas, but it's air, it's matter, right? Light waves can travel through that matter. They don't have to, but they can. Whereas mechanical waves need that matter, need that medium in which to travel through. Here's where the big difference, well, we already talked about one big difference between electromagnetic and mechanical waves. One, electromagnetic waves don't mean a medium, mechanical waves do. Another difference, how we determine how much energy they carry. Mechanical waves, we said, the amount of energy they carry is related to their amplitude. And that the amplitude of the wave is directly related to how much energy it carries. Not so with electromagnetic radiation. The amount of energy that an electromagnetic wave carries is based on its frequency and wavelength, which we said were two interrelated concepts. So electromagnetic wave radiation, different waves carry different amounts of energy. How much energy they carry is not related to their amplitude, is related to their wavelength and frequency. We will find that the amplitude of pretty much all electromagnetic waves would be the same. That doesn't determine how much energy they carry. The frequency and the wavelength determines how much energy they carry. Good there? Okay. Next, speed. Here's a weird one. Light travels way faster than sound does. Anybody know the approximate speed of sound? Ever hear, random piece of information that sticks in your head somewhere? It's really fast, okay? Sound travels at, depending on the temperature and depending on where you're, what part of the atmosphere you're in, it's in the range of 700 to 750 miles per hour, okay? Light, which is an electromagnetic wave, travels at 186,000 miles per second. So, a big difference there, obviously, right? One of those key things, or one of the ways that we can tell they're much different, it might happen later today when these thunderstorms roll through, right? An example of the difference between the speed of light and the speed of sound is lightning and thunder. Yes? We're familiar that thunder is the sound of lightning. Yes? Hopefully we learned that in like 4th grade. So, after you figured out that it wasn't just God bowling, so, which, it's all right. At the time, that's what your brain can handle, but, as we get a little more sophisticated, we have to, be a little more accurate with our description. Okay. Lightning is a light wave, or thunder is a sound wave. So you see lightning first, you hear thunder after that. Why? Because light travels way faster than sound. But what we find out is that speed of light in a vacuum, 3.00 times 10 to the 8th meters per second. So 300 million meters every second. And that rate stays constant as long as it's in a vacuum. We talked about that in the case of a mechanical wave, it's 8 zeros. Yeah, it's 3 with 8 zeros after, 300 million. Every second, remember, it's a second. Okay. We talked about that. The medium through which a mechanical wave travels affects the speed at which it travels. Which state of matter generally transfers mechanical waves the fastest?
Gas.
Solid. Why?
Is there more matter?
Yes. What does a mechanical wave need in order to transfer from the next matter to the next medium to the next medium?
Needs to be touching it?
Touching it, right? Contact. It's conduction. So in a solid, generally those waves travel faster because there's more contact, right? The medium does affect the speed of of an electromagnetic wave as well, but generally it causes it to slow down. So the thicker something is, the slower electromagnetic waves travel. Why? Because that matter just gets in their way, right? The windows in this room, light travels through those windows, but it doesn't travel through the windows as fast as it travels through the air outside or the air in here. It also doesn't travel as fast as it travels from the sun all the way to here, right? The less matter that's in the way, the faster electromagnetic waves travel. But they all travel at exactly the same speed in those different mediums. This is the fastest. This is the ultimate speed limit. And as I get more sophisticated with your discussion of things, stuff like that, we find out that this is the ultimate speed limit of the universe. Nothing goes faster than this, at least nothing that we've measured up until this point. So this value, 300 million meters per second, ultimate speed limit. Good there. The one thing that really gets me, like every time I think about this number, 186,000 miles per second. That's really fast, right? It's fast. That distance is approximately 6.5 times around the Earth every second. So whereas it takes a plane about 24 hours to fly one time around the Earth, approximately, okay? Light could travel 6.5 times around the Earth every second. So it's good.
How do you measure that?
Good question, Andy. So, let's go. The speed of light is measured by a guy named Albert Michelson, okay, in conjunction with other people. And this picture shows how he did it. Oh, sorry. Did we not get that part? Albert Michelson. M-I-C-H. No. For completely unrelated note, well, it's not completely unrelated, it's somewhat related. Albert Michelson and a guy that he worked with, Edward Morley, did a lot of their work actually in the Cleveland area at the Case Institute of Technology, which is now part of Case Western Reserve University. And I went to Case, that's where I got my undergraduate degree from. And the dorm that I lived in was right next to the Michelson dorm, named after this guy here. All jerks. Everybody lived in Michelson dorm, jerks. Every single one of them. So, so it was good when we beat him in like dorm Olympics and stuff like that. It was a good time. So they're just kind of cocky about it. So it was good. Anyway, so Andy, let's go back here. Let's take a look at this picture right here. Okay. You have a copy of this picture on the back of your sheet. Okay. All right. So speed. Speed is a relationship between two things. What does speed relate together?
Time and distance.
Time and distance, right? Not necessarily in that order, but time and distance, right? So in order to measure the speed of something, you got to know a distance and you got to know a time. The problem being that if light can travel around the world 6.5 times every second, the amount of time that goes by for it to travel a certain distance is really small. So measuring the time that it takes light to go a certain distance is a problem. It's way quicker than any kind of reaction time that, people have or whatever it is, right? So you have to devise a way to get a distance and get a time. So this is what they did. First, here's a little flashlight. And this is a rotating mirror. It's not a circle, it was an octagon, so it's got flat surfaces. When light from the flashlight hits the mirrors, what does it do? Bounces off of it, just like any other light that hits a mirror. So the light goes in and it bounces off of this mirror. If you have the mirror angled correctly, you can make it bounce any way you want to. Reflection, right? The angle it goes in equals the angle that it goes out. So you could angle this mirror just right that this light beam hits it and bounces to another mirror. Another mirror that might happen to be really far distance away. At least for us, 35 kilometers is kind of a far distance, right? It's, about 25 miles or something like that. But when that light beam hits the mirror over here, what's it going to do when it hits that mirror? It's going to bounce back. So it comes back pretty much to the spot that it started, except there's another mirror on the other side of this little rotating platform, and it's angled just correctly to hit this telescope. So the observer here is looking at the flashlight that happens to be, 3 feet away from him, but the light from that flashlight has traveled 70 kilometers in that time. Does that make sense? Now, how long does it take the light to get there? That's the trick. You can set these mirrors up and that's great, but you still don't have a time. How long does it take from when you turn on the flashlight for the light to get there? If you turned on the flashlight just, 3 feet away, you would see it almost instantly. So there has to be a way to get the time. You got the distance part, but now you need the time. So here's what they did. They took this set of mirrors and they started spinning it at a very quick rate. And when the mirrors spun at just the right rate, the light hit the one mirror here, went to 35 kilometers, came back, and it hit that same mirror. But it wasn't here, it was on the other side of the octagon. Does that make sense? Knowing the rate at which the octagon was spinning, you can calculate how much time it took this mirror to get from this side over to here. If it's spinning at, 3,500 RPM, 3,500 revolutions per minute, you can figure out how long it takes for this mirror to get from here to there. And you know that the light traveled 70 kilometers in that time. Now you have a distance, now you have a time, now you can calculate the speed of light. Okay. Does that make sense to you?
Yes.
So, it's a complex process, but because we're dealing with something that is so fast, we have to find a way that you can get distance and time. You think? So, actually, one of my labs in college, you actually do this on a smaller scale. Suzanne, the big thing being that you just have to have light bounce enough times that you can get a time from when you started it to when you get it, So same sort of thing. There was a little rotating mirror, blah, 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 blah. But instead of bouncing at 35 kilometers, there was some elaborate set of mirrors that we had set up on a big table in the room. And, it's basically just verifying it, but, to get the idea of what it looks like. So, all right. So last thing for today, and then we'll wrap this up here. So what we find out is that all electromagnetic waves, regardless if they are visible light, which is the one that's pretty most available to us, I wouldn't say most available, but kind of most important to us, or microwaves, radio waves, X-rays, all the different types of electromagnetic radiation that we will talk about tomorrow, all travel at the same speed, even though they have different wavelengths, different frequencies. They carry different amounts of energy, but they all travel at the same rate. All right, good there? Okay, tomorrow we will talk about the electromagnetic spectrum and all the different types of electromagnetic radiation there is, or are, I guess would be the better grammatical way of doing it. Right now the calendar does not have any reading or homework stuff. I will get that updated today, probably during fourth period. Not a whole lot, but just some things to think about as we go along. So I'll get that updated today, okay?